actually means many. So it expands to things beyond just binomials. You guys remind me though, a binomial that we learned about last time. How many terms does a binomial have? Yes, but actually last class we learned about monomials. How many terms does a monomial have? Okay, good. I thought, no, wait a second. Why are they all answering wrong? Oh, wait. I just wrote the wrong thing. Now, you guys, so I'm assuming that those of you who knew the right answer, that binomial had 2 terms, looked at the fact that this word in front does change sometimes to signify how many pieces, how many terms. So mono means 1, bi means 2. Tri, how many? The trinomial is 3. Etc. They don't really go, I mean, I guess that they'll say quadratic, but they won't go a lot further. In fact, polynomial is the most popular thing to stop with, and beyond that, you just say polynomial. So beyond trinomial, really, you would start to hear polynomial. And any of these things previous to polynomial, the binomial, the trinomial, whatever, they can all be categorized under that one word. So we're going to start playing with any variety of those. Okay? As I start to use the vocab, just know that we can go back and forth comfortably. The polynomial means however many. So the stuff we've already described, or lots more. It can have tons of pieces. Who cares? The same rules will continue to apply. That's the point. The same stuff you're learning on the small, easy ones will apply if you were to one day in your life model something with lots of constraints. As far as the way a polynomial is written, usually we write it with the first piece, the leading term, being the biggest power. So we like to write them in general, usually write in descending order. In other words, our first piece called the leading term is usually the biggest. And remember last time we did discuss power sum. We said that that largest power actually had another name. What is it? It describes the shape of the function, but if I took the power off of the largest power off of any piece, what do I call that number, that value? The degree. Remember? We said that we have this naming scheme of binomial, trinomial, polynomial, that as far as knowing the behavior, as far as knowing how many curves you see on the model or on the picture, the way you do that is by looking at the degree, the highest power of any piece, of any term. And remember, if you have more than one power, what do you do to get the degree? You add those powers. If you had an x and a y, you'd add those powers on there to get the degree. Okay, good. A lot of times, what this part I've written in black is saying is, hey guys, a lot of times when you see these things being written, they're going to start with highest power and count down. They're not going to mix up the pieces. It doesn't change the way it behaves or anything. But just a pretty way to write it that you're usually going to see is where the first thing is the highest power and it counts down. That's kind of the rule of thumb. So, for example, if I wanted to write for you a trinomial, I could say 2x squared minus 4x plus 3. That's an example of a trinomial, which is a type of polynomial. It has 3 pieces, 3 terms. Do you guys see that? 3 chunks. The 2x squared is the first piece, The minus 4x is the next piece, and the 3 is the last piece. And notice, again, it is rule of thumb. The powers on those x's, see how I have a 2 and then I go down to 1 and now I have none? I counted down. So these have been written in descending order, where they go down, the powers do. And this leading term, this front piece, is kind of special. It has the degree on it. What's the degree again? 2. Which tells me it has how many curves? 2 minus 1 is 1. Okay, so the reason we care about the degree in real life a lot of times is because we can figure out it has 1 curve on the model. If you were graphing it, you'd know what to expect, and you will be graphing some tonight, so that's good. Something else special that you can pull off of this. Later on in math, you may be worried about something called the leading coefficient. Well, the 2 minus 1, basically you always take the degree and you always take away 1 from it. So if it had been a 4, it'd be 4 minus 1, 3 curves. If it had been a 5, 5 minus 1, 4 curves. Always, yeah. If you want to predict how many curves, take away 1. Now, I have to be careful, Taylor, because in this example and in what I'm really referring to the most, we have only x's. If I started messing with the x's and the y's, our model would start bending in multiple dimensions. It would start getting curves on different sides. So the best time to do this with the degree and actually get an accurate answer is when you're using just one variable, one letter, one-dimensional space. When it gets bigger, it'll start bending it differently. But the idea that I was starting to talk about here is leading coefficient. That was good, Taylor. I could tell some people may not have remembered that also. So I'm glad you asked that. So the leading coefficient, though, this is something else behaviorally, in addition to the degree stuff we just talked about, that can help you predict things. You won't learn about it yet, but if you take 0, like 161 later or higher, you may talk about something called a leading coefficient and how it affects your model. This is the leading coefficient. Remember back when you were learning about terms, you had something called a coefficient and something called a variable? The coefficient's always the number piece, right? Do you remember this? So the idea is that the number in front of the leading term, the front number, is the leading coefficient. It's the one in front. So that's what we call it. And it is one that's of a little bit more significance. It does change the behavior with more impacts than the other numbers. Because it's beside the strongest variable. The variable is making the most impact on our shape. This number 3, just for your information, is the constant term. And you guys are probably pretty familiar with that. Back when we were modeling cost functions, for example, we a lot of times had a fixed cost or a set cost or constant cost, and other times we have a variable cost, right? Back in previous chapters. So just like before, that 3 would have been something we may have called a fixed cost. Normally when it's not just a financial problem, we'll call it constant. Because there's not a letter attached to it that's going to make a change. The 3 is considered a constant term. The leading coefficient in the front is where most of that change is coming from. You can think about it as like a train. And the one on front, that's leading the way. That's dictating the most of this problem. So we will later in mathematics care about that leading coefficient, that number, and the degree on that, because it will change how it bends. Very cool. Now in this class, especially in this session, we won't go into that much. It's just that since you're learning about what is a polynomial, we explore some of the terms, so later on you're more prepared to play with it if you take a different math class. What we're going to do tonight is just talk about how to evaluate them, graph them, and how to add them together. Done. It's going to be that easy. So evaluate. That sounds like a hard thing, but guess what? It's super easy. You're going to love it. Maybe. No, I'm kidding. You'll love it. Okay. So, it's because the word evaluate sounds scary. That's why I was having fun with you guys. Okay. Evaluate polynomial functions. That's our first objective. So here's the deal. You guys have already done this. That's why I'm telling you it's easy. All you do is we're going to use functionalization to plug in. And it was Brittany's favorite thing ever. She's so happy we're doing it now. I'm just kidding. Don't you guys love how I do that? Okay, I'm just kidding. So, let's say, for example, you had some polynomial. Let's call it P of X for polynomial of X. Oh, we're being creative now. We used to use F of X for function of X. Anyway, got to keep it real. Okay. So here's going to be our polynomial, meaning function with more than one piece, attached by pluses or minuses. Here we go. How many terms does that thing have, by the way? How many? Too many. Okay, wrong answer. 4. Come on, we can count these. Okay, 4 pieces. What's the degree? Since we only have one variable, the model is really easy to predict. How many curves am I going to have? 3. 4 minus 1 is 3. Good. What's the leading coefficient? -2, because it's been written in the proper order, right, where the powers count down. And just out of curiosity, what's the constant term on this example? Good. -8. Perfect. So, we've got that stuff squared away. We're good at talking about this stuff and predicting stuff about it. Let's see if we can evaluate. For example, if I said, hey guys, for X, I'm going to say that X is equal to 2. Evaluate the polynomial for this value of X. Or evaluate this polynomial for P of 2. That's the same way, right? Remember, that's what functionalization does. Notice the only thing in the P with parentheses that's changed is the X was changed to a 2. So that means that in the polynomial, everywhere I have an X, I'm going to instead write what? 2. Okay, good. So let's rewrite it so that we can actually simplify it. So we have 2. Remember, I tend to put things in parentheses a lot because if you have something funny like a -2, it could cause problems if you forgot the parentheses. But that's your call on how organized you want to be. So everywhere I have X, I stuck in a 2. Guys, remind me, this stuff on the left, this P with a 2 in parentheses, does that really mean a lot to me other than just what X is? No, I'm not trying to multiply or divide off that or nothing crazy like that. It's just notation. It's just a symbolic way of saying, hey, replace your X with 2, nothing more. So all that I really focus on is the right-hand side. I just focus on, okay, now the 2's there, let's simplify. Order of ops, let's work this thing out. -2, I'm going to do the powers first. 2 to the 4th, what do I get? You have a calculator, by the way, but we will have fun and take it slow. 2 times 2 is, okay, okay, good. 16 minus 5, just checking. No, okay, 2 to the 3rd is 8. Plus, I'll just write this. So I took care of my exponents in one smooth step. Now let's go through and multiply. Again, you have an order of operations calculator. You do not have to show me steps. I just want to make sure people viewing this understand what's going on here. -2 times 16 gives me what? -32, okay. And I have a -5 times 8. That gives me -40. -4 minus 8. Okay, can we just put that together? What do we get? Somebody tell me the answer. P where 2 is put in for X is equal to what? Sounds like a plan. So when I say evaluate, that's it. It sounded so hard, so I was having so much fun with that mental game on you guys until I wrote it on the board and you saw how easy it is. Even though they're using big words like evaluate, you're just plugging in a number for X like you've always done. So,